All right, welcome back to Algebra 2. We're going to continue on with our probability notes. So we're going to look at Unit 9.2. And this is on the probability of compound events. So two symbols that are used in probability. The U means union, which means or problems, or means both. We want this and this to occur. And then the upside down U is the intersection symbol, and that's usually what's in common. Okay, so we have two things and there's an overlap. If you were to see maybe a Venn diagram, there's an intersection part. All right, so there's three different kinds of compound events that we're going to be looking at. Two of them are or problems, so it has the word or in it, and then one of them is an and problem. So the two that have the word or in it, the first one is if A and B are mutually exclusive, meaning there's nothing in common. Okay, so mutually exclusive, nothing in common. So that's A union B. So again, that U means or. So if we want to find the probability of an event happening that are mutually exclusive, we would take the probability of A occurring, the first event, and then add on the probability of B, the second event. So we just add those two together. All right, the second kind, again, it's an or problem, but they're not mutually exclusive. There's something that's in common, something overlapping between the two events. All right, and so the formula that we would use is the probability of the first event, A, plus the probability of the second event, B, just like we did on the first one. But then what we're going to do is subtract off the probability of what's in common, okay, the intersection. Now, what I usually do is I can combine those first two together and not even worry about the first one, and just always remember the second one. So you're always adding the first two probabilities together, then look to see if there's something in common. If there's nothing in common, then you don't have to worry about subtracting anything off. But if there is, then you would subtract something off. Now, the third kind is an and problem. It has to have the word and. I want it to be this, and I want it to be this. Okay? I want it to be an even number, and I want it to be a 6, something like that. So then what we do is do the intersection, or just think of, we want to take the probability of just what's in common. All right, that's our overlap. That's all we're looking for then. All right, so I have an example for each one so you can kind of see it in words in the actual problem. So example 1, a card is randomly selected from a standard deck of 52 cards. What's probability that is an ace or a face card? All right, so we can see the word or in it. So if you look at these cards in a Venn diagram, so the first event, probability A, is our aces. So you can see in the first Venn diagram all the aces. There's 4 of them. Right? And then in the second circle Venn diagram, all the face cards, and there's 12 of them. And you can see that there's nothing in common with aces and face cards, and it has the word or in it. So what we do is we just take that first formula, take the probability of the first event happening, A, and then add on the probability of the second event happening, B. All right, so the probability of A would be 4 out of 52. There's 4 cards that are aces, 52 cards, plus all the face cards. There's 12 out of 52. Again, there's no overlap, nothing in common. You just add those together. So 16 out of 52. When you write this stuff out, since the denominators are already the same, you want to just keep them the same. Don't try to simplify each separate fraction and then add them together. Because you're adding fractions and you need denominators to be the same, just leave them. All right, and then you'll simplify at the end. So you're just adding the numerators together. So again, we can divide. Let's see, I think 4 goes into both of those. So that's going to be 4 out of 13. All right, example 2, card selected, again from a standard deck of cards. What's the probability the card that we pick, one card, is a heart or a face card? Heart or a face card. So in the first diagram, we have all the hearts shown. So again, you want to make sure that you know how many hearts there are. There's 13 of them. And then in the second diagram, or the Venn diagram, there's all the face cards again. Again, there's 12. And we can see that there's an overlap. So there's 3 cards, the Jack, the Queen, and the King, that also have hearts. There's 3 of them. And the word or is in between the two. So we have to use the formula where we add each of the probabilities together separate and then subtract off what's in common. All right, so the probability of getting a heart, 13 of them out of 52, plus all the face cards, there's 12. And we're going to subtract off what's in common. There's 3 cards that are in common with both of them. All right, so then we can add the numerator, 13 plus 12 is 25, and then subtract off 3, so that's 22 out of 52. And we can divide by 2, so that's 11 over 26. And then example 3, cards, again, randomly selected from a standard deck of cards. What's the probability the card is a Jack and a red card? All right, so kind of think how this would look. Okay, you can look at, you know, in the Venn diagram, you would have everything, the Jacks and the reds, you know, what's in common is all we're looking for. So you could list out this Venn diagram, but remember, this is an and problem, not an or problem. So all we're looking for is the intersection part. So you want to ask yourself, well, how many Jacks are red? Okay, so you look at your deck of cards. There's a Jack that's a diamond, and there's a Jack that's a heart. Right, those are both red and Jack, and so there's 2 of them. Out of 52, and we can simplify this down to 1 over 26. All right, so make sure that on these kind of problems you're looking when you're selecting one card or one number, one color, something like that, and there's 2 events happening, make sure you look at the word in between. Does it have the word and, or does it have the word or? Right, so we have 2 events, but separated by the word or it's going to be and. That tells us that we're adding or finding intersection or adding and subtracting. All right, so complements occur if we don't want to kind of go through and count up everything that we don't want to occur. So usually the word not is in the problem. So I don't want it to be a multiple of 5. I don't want it to be an even number. So what you can do is take the total and total number of choices and subtract off the probability of the event happening. All right, so in this symbol here, or this formula, that A with the little, I guess apostrophe, that means not happening. So the probability of event A not happening is equal to 1, or the total, minus the probability of the event happening. So the probability of not doing something is equal to 1 minus the probability of actually doing it. All right, so example 4, when 2 six-sided die are tossed, again, there's 36 combinations. Part A, what's the probability of not rolling a sum of 4? Okay, what's the probability of not rolling a sum of 4? So you could go through and add up all the ones that are not going to add up to 4. Right, and that would be your probability, all over 36. Another way that we could do this is, let's go ahead and find the ones that do add up to 4 and subtract it from 36, because again, there's 36 combinations. So again, what's the probability of not doing something? Okay, So not rolling a 4. So if we go to the 4s, so here's our 4s right here, there's 3 of them. Okay? So if we take the total number of choices, 100%, 36 combinations, and subtract off the 3 combinations of adding a 4, and divide it by the total. Right? So there's 3 ways of rolling a 4. Well, we don't want those 3, so we're going to subtract those off of 36. So now that we can see there's 33 ways to roll something other than a 4. And then we can simplify this down. All right, so 11 out of 12. All right, B, what's the probability of not rolling doubles? Not rolling doubles. So again, the easiest way to do something, again, because it's not, is find out how many ways can you roll a double, subtract it from the total, that's your numerator, and then divide it by the total number of choices. Again, this would be 36. All right, so again, our doubles occur along this diagonal here. There's, again, 6 of them. And so we don't want those 6. So if we take those 6 out of the total combinations there are, that's going to leave us with 30 over 36. And if we divide by 6, 5, 6. All right, and then let's go ahead and answer each of these questions. A card, one single card is randomly selected from a standard deck of 52 cards. What's the probability that is not an ace? Okay, so again, if we look back at what the picture of all the cards look like, there's 4 aces, and we don't want those, but we want any other card will work. So there's going to be 48 that are not aces out of 52. Divide by 12. So 12/13. B, what's probably that the card is not a face card? Not a face card, so that we know there's 12 cards that are not face cards. Or sorry, there's 12 cards that are face cards. So we're going to take our total, 52, and subtract off the 12 we don't want, 40 out of 52. So 10/13. What's probably that the card is a 5 or a 6? So we have the word or in there. So we're going to be adding these probabilities together. So the total number of ways of rolling of selecting a card that's a 5, there's 4 of them, plus all the ways to roll or to pick a 6, there's 4 of them. And there's no single card that's both 5 and 6, so we don't subtract off anything. There's nothing in common, no intersection. So we add these together, so that's 8 out of 52. And then again, we want to simplify, so 2/13. All right, D, what's probability the card is diamond and a jack? So we have the word and in it. So we want to find the intersection between these 2 events. So how many diamonds are also jacks, or how many jacks are also diamonds? Well, there's only one card that's both. It's the jack of diamonds. E, what's probability that the card is a 4 and a queen? All right, so how many 4s are also queens, or how many queens are also 4s? There's none. So there's no probability, or the probability is 0, that you're going to pick a card that's a 4 and a queen. And then F, what's probability that it's a 4 or a queen? So this has the word or in it now. So or we're going to add. So how many 4s are there? There's 4 of them. Plus, how many queens are there? There's 4 of them. And then we want to check real quick, is there a card that's both 4 and queen? No, there's not. So we don't subtract anything that's in common. So 8 out of 52. And we can simplify that down, divide by 4, so that's 2/13. Okay, so that's it.